Hi guys, we are going to take a look at equilibrium expressions in this set of notes. Make sure you've got the notes page printed and you're ready to fill them out. So as we've seen, the equilibrium constant, which is represented by K, is a value that represents the ratio of product to reactant concentrations at equilibrium. So this has been discussed when we were talking about reaction quotients, but we haven't looked at how we actually find equilibrium constant. So now we're going to do that. We symbolize it by K, and it has that little EQ that can just represent like general equilibrium. We can put a little subscript C there to represent concentration, and then it says it can also be reported in terms of pressure, and we can put Kp. To calculate the equilibrium constant, we can first set up the equilibrium expression and then plug in the concentrations or pressures of chemicals at equilibrium. The equilibrium itself can also be useful in terms of other calculations. So equilibrium is expressed through an equilibrium expression and an equilibrium constant. The expression for the reaction, and we're given this kind of generic reaction, is, and we have two expressions here. Now, hopefully these look really familiar. They are the same expressions we used for QC and QB. Same exact setup, products over reactants. The only difference here is our labeling. So we're labeling it K, which means that whatever values we plug into these expressions must be at equilibrium. So it should state that in your problems. So I'll say something like the concentrations of the chemicals at equilibrium were, and give you those concentrations. So now we know for sure that what we're plugging in is at equilibrium. We're not trying to figure it out like we were with Q. Okay? So a little bit different setup there, but the same, or different idea, but the same exact setup, which makes our calculations that much easier. We're not really learning a whole new calculation, just a different way of interpreting the values. So we're going to do a little practice with this. We've got a kind of different looking graph set up here, but we have a data table with it. So this is for the reaction that is shown down here. So the reaction of carbon monoxide, CO, chlorine, Cl2, forms CoCl2. And that reaction is shown in the graph. So we're going to start by just looking at kind of the first time period that happens here. So we're going to start with looking at the first 15 seconds. So we're going to be kind of looking, let's just take a glance at our graph at 15 seconds. So we start with a high amount of CO and Cl2 reactants, and we can see they're decreasing over time. And we start with no CoCl2, and it's increasing over time. And then when we hit 15 seconds, these have really stabilized and hit that horizontal. So we hit our first equilibrium right there. Okay. So at 15 seconds, we hit our equilibrium. So first thing we're going to do is part A. I'm going to do all my work over here. You've got space on your page to do it right underneath. It just wouldn't fit properly on the slide. So for part A, we want to write the equilibrium expression. So this is something that's asked a lot, is just to write the expression, not necessarily to jump into your numbers and calculating. Now, whenever you write these expressions, you do need to have a left side of your equation. These are in terms of concentrations. We can see that in our data there. And we're going to do it just like Q, so products over reactants. So we've got CoCl2 on the top, our product, brackets for concentration. Its coefficient's 1, so we don't need an exponent. We're going to divide that by our reactants, which is CO and Cl2, both raised to the first power. All right, so that's our expression. This is something that is asked for you to write on the AP exam, and yes, it is important to have a left side of your equation. If you don't have that, then you haven't written an expression or an equation. You've written just a ratio if you only write the right side, okay? You must write both sides. All right, we've done part A, check. Part B is to calculate the equilibrium constant for the reaction in the graph when it reaches its initial equilibrium at time equals 15 seconds. So when we hit that first horizontal, that first flat line, we're going to find our equilibrium. Now we could also do this, here at like 17.5 seconds, that kind of thing, because it's still horizontal there. We get those constant concentrations. So we're going to plug in our values into our expression. So at 15 seconds, we have COCl2 is 0.75. And on the bottom, we've got CO is 1.75 times Cl2 is 0.55. All right. So if we plug that into our calculator, being careful with this bottom part, either put big parentheses on the outside and your times in the middle, or the way I like to do it is 0.75 from the top divided by 1.75, and then I hit enter, and then I hit divide 0.55, just so I know both of those things on the bottom are being divided. Be careful with that. We should get 0.78. Okay, and we're going to talk about what these signify a little bit more on our next problems on the back, but that is our equilibrium constant. So we can see though that our graph continues and we get some more action happening here. So at time equals 20 seconds, so we can see here at 20 seconds, we have this kind of crazy jump in that red CO line. So more CO is added to the reaction container. So that's why it jumps up, making its line jump to a higher concentration. Then equilibrium is reestablished. So we add a chemical, which means our reaction has to kind of rebalance itself, has to get back to its equilibrium. So we say it's reestablished. We want to calculate the equilibrium constant for the reaction in the graph when the second equilibrium is established at 25 seconds. So we're going to recalculate this equilibrium at 25 seconds. So same equilibrium expression, we're just plugging in different numbers. So COCl2 has gone up to 0.79. So we've gotten a little more product. And then our CO obviously went, wrong part there. Our CO obviously went up because we added more, so it's 1.90. It went up and then dropped back down, so you can see that in that graph. And then we get 0.53, which is a little bit lower than the previous problem up here. So when we calculate our K this time, we get 0.78 with our sig figs. Well, that's interesting, right? We get the same value for our equilibrium in part B and part C. So that's interesting, right? Part D says compare the values for the equilibrium constants at those two times and explain their relationship. So number one, they are equal. So how can we explain this? Well, equilibrium constants, which are K, are the ratio of products over reactants, right? The ratio will be constant because the reaction, RxM for reaction, will always return to equilibrium. Okay, so the idea of an equilibrium constant is that it's a constant, right? So no matter what our reaction does, no matter what we're going to mess with it in terms of concentration up here, we can change these concentrations and it's going to get back to equilibrium. It's going to get back to the same ratio of products to reactants. We can see that to do that, when we added more CO, we jumped it up, it fell back down. It got used up a little bit. And it used up just a little bit of that Cl2 as well. And when it was using those up, it was making this COCl2, right? We had to make some of that. So that reestablished the same ratio of products to reactants and got us back to equilibrium, okay? So it's this whole idea of ratios. Now, we can change that equilibrium constant for a reaction, and the only really way we can change that constant is to change temperature, okay? If we were to change the temperature of our reaction, that increases the speed of all the particles and adjusts our equilibrium, and it will actually change our equilibrium constant. That is not something we do a lot, but it does happen. All right, so now flip to the other side. We're going to look at the value of our equilibrium constant and what it does. So it can help show which chemicals, either reactants or products, are present in higher concentrations in equilibrium. So if we're only looking at the constant once we calculate it, we can actually predict if we have more reactants or more products, and it's based on that value. So if we think about it, if we had equal ratio of products to reactants, K would equal 1, right? You could simplify this ratio, we get 1 to 1. So if K is equal to 1, it means our concentrations are equal at equilibrium. Now that doesn't happen too often, okay? Typically, we're going to have more products or more reactants. So if our equilibrium constant, K, is greater than 1, that means we have more products at equilibrium. Okay, more products are present at equilibrium. That means we have a larger numerator, right? We have more products than we do reactants. So if we have a larger numerator, we're going to get a bigger value for K. It's going to be greater than 1. So that tells us that we favor the products, means that we're going to have more products than reactants. So if you think about our reaction, we're going to have a little bit of reactants and a whole lot of products. Okay? If our KEQ, our equilibrium constant, is less than 1, then that means that we have a larger denominator. So this one would mean that we have a little bit of product and a whole lot of reactant. Okay? So it favors the reactants in that case. So once we calculate our equilibrium constant, we can see really what side is favored. And if we don't have to calculate, if we're given our equilibrium constant, we can predict which side is favored in the reaction, and that can give us some info about what's going on in that reaction as well. All right, let's try one. So first we're going to write this equilibrium expression, and this time we're going to write it in terms of pressure, so we're going to practice with that one. So if it's in terms of pressure, we label it P, Kp, and then we're going to put everything in terms of pressure. So still products over reactants, but it's the partial pressure of NH3 squared, because of that coefficient, divided by the partial pressure of nitrogen times the partial pressure of hydrogen. And we're going to cube that one because of its coefficient. So there is our expression, again, making sure that we write both sides of our equal sign, not leave anything out. And we're using parentheses with pressures and not brackets. So you can remember that, parentheses with pressures. It's also on your equation sheet in terms of pressure. So you have a reference for what it looks like. So we're not just guessing here, okay? You have something to look at on your reference sheet for pressure versus concentration. Now, we want to calculate Kp here. So we're going to plug in our pressure values. You can see all of these are in terms of atmospheres, so we want to find that pressure. All right, so NH3.010, we're squaring it, divided by nitrogen is 3, times our hydrogen, 1.50. And we're cubing that one. All right, again, really good to practice in your calculator. When I put this in, I would type in 0.01 squared and hit enter. Divide 3, enter. Then I would put divide, because again, your 1.5 is on the bottom. I'd put parentheses, 1.5 cubed, close my parentheses, and hit enter to make sure that this is being cubed properly. When you do that, you should get a pretty small number here. We get 9.9 times 10 to the negative 6. This is a really good opportunity to put it in scientific notation because no one wants to write 5 zeros. This is silly to write that, okay? So now we want to determine, I know the question's not here, but what's favored, okay? So we're going to look at this value. Now, we don't just look at the front part of the number if it's in scientific notation. That doesn't give us a lot of info. It's that exponent that we want, right? We want that exponent. So if it's 10 to the negative 6, that means we've got a decimal and then a whole bunch of zeros, right? It's a very small number. So that means it's less than 1. So when our K value is less than 1, that means our reactants are favored. Okay, we're favoring the reactants. We can also see that in our numbers here. Our reactants, the nitrogen and hydrogen, have much bigger values than the numerator, that ammonia, NH3. Okay, so we're favoring those reactants. All right, last part. So something that we can recall from the the reaction quotient stuff we did is that we leave out the pure solids and liquids in our expressions. So we want to make sure we're practicing that as well. So first thing here, again, we're going to write our equilibrium expression. Nothing indicates that it should be in terms of pressure, so we go ahead with concentration. So we've got products. We've got hydrogen, which is a gas. We've got carbon monoxide, which is a gas. We've got water as a gas. And then we've got carbon as a solid. So we are not going to include it in our expression, right? It is not a aqueous solution or a gas, so it doesn't really have a concentration, okay? It's just like a mass. So our equilibrium depends only on those chemicals. There we go. Okay. So Kc equals, we're going to plug in our values. So we've got, they give us water, so let's go ahead and put that on the bottom. We've got hydrogen times 1.50. Do my parentheses, I like it better. All right. And we want to calculate our equilibrium constant. So pause it, calculator, and then come check. All right, we do have 3 significant figures, so we should get 1.88 for our equilibrium constant. Now that one's a little bit bigger than 1, pretty close though. Since it's bigger than 1, we would say that our products are favored, okay? Now, our last part is finding the concentration of water in the reaction if our hydrogen and our carbon monoxide both equal 0.75, and this should be molar. Missing that unit there, little typo. So this is kind of the last type of thing we can do. So given our equilibrium constant that we calculated in the previous question, we can find the concentration of one of our chemicals if we have a concentration of everything else. So I'm just going to first plug stuff in to this equilibrium expression at the top. So our equilibrium constant we just found was 1.88. Our question says hydrogen and carbon monoxide are 0.75 molar. Now, since we're multiplying 0.75 times 0.75, I'm just going to write it as 0.75 squared. Right? Same value. And we want the concentration of water. Now, first thing I'm going to do here is do a little switching. If I want to solve for this denominator, I need to move it to the other side. So I'm going to multiply by my concentration of water on both sides so that we can get it out of that denominator, right? And then the second thing I'm going to do, I'm going to change colors again here, is I'm going to divide by this 1.88 on both sides. 1.88, we'll stick it on the bottom here, so I can get it to the other side. So they're basically switching sides, right? So what we end up with is water equals 0.75 squared over 1.88. Now all our numbers are on one side, our water's on the other, and we can calculate. So we get 0.75 squared over 1.88. We should get 0.30. This is looking for a concentration, and concentrations do have units of molarity, so we want to stick that on there. And that would be our answer. Okay, so we can also use our expression to find the concentration of a specific chemical at equilibrium. So it's another capability of using these equilibrium constants once we have them. All right, you guys have the practice that's posted on equilibrium expressions. So work on that next. And if you have questions, let me know. Thanks, guys.